Hey folks, in this short video, I want to go over some quizzes about these proof trees and derivations. Um, uh, the right order to watch this in may vary depending on sort of the way that you like to learn. It may make sense to watch this after watching the whiteboard lecture on derivations. It may make sense to do it in the other way. I'm going to post it now because this is where it comes in the file. Um, okay, so for all of these, I'm going to ask you about the number of different proofs. So we've asked these questions for data types, but we've asked questions like how many different, nats are there? Or if I give you this data type, how many different ways to build a thing are there? We've seen those kinds of questions a bunch. Now I want to focus on, okay, how many different ways are there to build proofs using these notions of evidence? So I've set up the screen so that we can see the inference rule presentation here, and we can see the inductive presentation here. So sort of choose your own adventure there about what you think is the easiest way to see what's going on. Let me get that centered. That's probably best. Okay, great. Okay, so first question. How many different proofs of EV0 can be built using combinations of the constructors EV0 and EVSS, right? Given this EV type, how many different ways are there to prove EV0? Pause the video. So I would say the right answer here is 1. There's only this proof, right? EVSS will only give you proofs about higher numbers. So once you've got a proof of EV0, if you ever apply EVSS, you're now talking about proving something higher up. There's only one proof that 0 is even. What about EV1? How many proofs are there that 1 is even? Pause the video if you need to. Now, we don't yet know how to show it, but the answer ought to be 0, right? If this is a good definition of evenness, there should be no proofs that the number 1 is even. What about for EV2? Pause the video. So again, the argument I made for 0 is I think really similar. How many ways are there to prove EV2? Well, EV0 proves you that 0 is even, and then EVSS shows that 2 is even, and then any more applications of EVSS, which is really the only move we have after we've made our EV0 move at the bottom, is only going to get us larger numbers. So again, I'm going to say there's exactly one proof. Okay, let's generalize. What about for an arbitrary natural number n? How many proofs of EVn are there? Read the answers carefully. Pause the video if you need to. So for the first one, we're saying, look, it depends on the value of n. There could be any finite number of proofs, including 0. Depending on the value of n, there could be some finite number of proofs, including 0, or infinitely many. At most 1, exactly 1, or 0. So the answer I would give here is at most 1. We already saw in the argument for EV0 and for EV2 that there's only one way to prove that a given even number really is even in the rules that we've come up with. Now, numbers that aren't even, like 1, 3, 47, take your pick, there's no proofs that those odd numbers are even. We certainly hope. We can prove it later. So there, I think the answer is at most 1. Here, it's not any number, any finite number, right? It's really either 0 or 1. And it can never be infinitely many in the setup we have. And it's not exactly 1 because some numbers aren't even, and it's not 0 because some numbers are even. Okay. Next, we have some hypotheticals. They all concern this potential extra rule we could add. Let me put it in inference rule notation in case that makes more sense to you. This rule is saying, look, you give me a number n. If it's even, then I can prove that the predecessor of the predecessor of n is even. So now we ask the same question we just had up here. How many proofs, if we extend the EV proposition, if we extend it with this rule, how many proofs of EVn are there for an arbitrary n? So here the right answer is 2. There could be either 0 proofs or infinitely many proofs. How many proofs would there be that 0 was even? Well, you'd have EV0, but you would also have EVPP of EVSS of EV0. because every EVSS could be canceled, and then we would have a different proof, right? One proof would look like this: EV0, EVSS, EVPP. And then another would look like this. And then another would look like EV0, EVSS, EVSS, EVPP, EVPP. That's one proof. Here's another proof. Now, I'm not saying whether or not this is a good idea. I'm just saying, look, now all of these would be distinct proofs that 0 is even. What do I mean by distinct proofs? I mean, well, look, the conclusion's the same, but the way we got there is really different. So in one proof, we'd say just apply V0. And another would say apply V0, apply VSS, apply VPP, right? Or the opposite order, right? Or we'd say this, or we'd say this. All these would be different proofs. Okay, two more. Suppose we add EVPP, and then we removed EV0. Now how many proofs of EVN are there? This is, I think, a very tricky one. So at this point, we would really only have two constructors for proving things, two forms of evidence. We'd have EVPP, and we would have EVSS. And that would be it, right? Those would be the only parts that we would have. So the problem there is like both EVSS and EVPP require you to have proved EVN before it gives you a proof, which means there's nowhere to start. There's no ground to stand on. It's like defining gnats but not having 0. Sure, you've got the successor operation around, but what are you going to use it on? So the answer here, if we, in this scenario where we only have EVPP and EVSS, the answer is 0. Okay, what about this one? Suppose we do the same thing. We drop EV0. How many proofs of this theorem would we have? So the answer here is infinitely many. This is, I think, a confusing situation. We could come up with a wrong definition where we'd get to prove a fancy theorem about nothing. There would be no n such that EVN, but we would say, look, if EVN, then EV4 plus n, sure. Why would there be infinitely many proofs? Well, one proof would be like what we saw before. You do EVSS, you do EVSS again, and you're good to go. But you can do EVSS, you can do EVPP, and then do another EVSS. Right? You can kind of zigzag, you can go up and down as much as you want. And you'll be able to do a bunch of different unique proofs that if a number n is even, then 4 plus n is even. Now, it would be about this bad definition of evenness. Without EV0, there's no ground to stand on, so all of your proof tree towers just float in air, right? There's no actual proofs there. But the answer here is infinitely many. Okay. There is a chance that you just got to the end of the video and you have a feeling like, you know, I made some good guesses and I made some bad guesses and I have no idea what Prof. Greenberg is talking about. And I'm sorry. What might be worthwhile is forget about it. Don't think about it. Watch a couple more videos, watch the bit on the whiteboard, get a little more comfortable doing proofs with these inductive propositions, and then go back and watch this and see if your intuition has been honed just a little bit. I think this is a worthwhile thing to think about now, but there's a chance it doesn't make sense to you, and I think that's okay. Just be patient. Okay, talk to you soon.